This is a presentation on the two-envelope paradox by me, Ed Meyer. The two-envelope paradox consists of two envelopes. One of the envelopes has twice as much money as the other. That's a given. You pick one randomly. They're identical envelopes. You open it. You find $20. You now have $20. What could the other envelope have in it? When I ask questions like this, you can pause it and think about it, which is what you should be doing. It's either $10 or $40. It's either half as much or twice as much. The question is, would you buy the other envelope that has 10 or 40 for your $20? So, here's a similar problem. You take $20 out of your wallet and you play the coin flip game. If it's heads, I give you 40. So now you have a profit of $20. If it's tails, you still get money. I give you $10. So you either win 40 or win 10, and you're paying $20. This is a good deal for you. It's important to understand this. You're risking only $10. You're paying 20, but the worst case scenario is you get 10 back for a result of minus 10, or you win 20. It's an even money proposition, and you either lose 10 or win 20. And if you want, we play it 100 times. You pay $20 each time. That's $2,000 that you paid. About half the time, it's going to be heads, and you win $40. So now you have $2,000 from when it's heads. And about 50% of the time, it's tails. And when they're tails, you get $500. So that's a total of $2,500, and you paid $2,000 to play. That's a profit of $500, which is a 25% gain. This is a good investment. Everybody agrees with this. There's a lot of controversy about the solution to the two-envelope paradox, but everybody agrees that paying $20 for a 50-50 shot at either 10 or 40 is a good deal. Now let's do the same thing again, but let's not open our envelope. We'll just do a theoretical analysis. How much is in your envelope? You don't know what's in there, so we're going to call it X. There's two equally likely possibilities for the other envelope. It's either half X or 2X. So what's the average amount of money in the other envelope? If there's X in your envelope, what's the average in the other envelope? It's 1.25X. Your envelope has X. The other envelope has an average of 1.25X. You picked the wrong envelope. You should have picked the other one. In the first thought experiment, we opened up the envelope and found $20, and then we said it's a good deal to trade because the other envelope has, on the average, 1.25. Now we could do the same thing without opening the envelope. The other envelope is better. This is the paradox. Of course, this makes no sense. How could one unopened envelope be better than the other one? And then once you make the trade, you can say, well, there's Y in my envelope. The other envelope has an average of 1.25Y. And you switch back. So this paradox has a long history. New publications appear each year. Here's the original one, 1943, and a bunch of publications. What are these papers about? Who is writing them? Is the paradox solved? People are writing about the two-envelope paradox in a variety of disciplines: philosophy, business, mathematics, physics. Two-envelope paradox is of wide interest. Various fields: game theory, probability theory, decision theory, of course, risk management, economics. It's hotly debated, but no consensus in the literature. There are some published solutions, which I put in quotes. Some claim that you can't have two envelopes in which one has twice as much money as the other, because infinity is a possibility. So anytime you open up the envelope and get non-infinity, then you're disappointed. And there's no uniform probability distribution over all the real numbers. This is true. So You can't even ask the question. These guys aren't solving it. They're just saying you can't even pose the question. Doesn't even make sense. There's another camp that says there can't be 1.25x in the other envelope. And then they spend the entire paper trying to explain why. For example, this comes to 5/4 x, which is more than x, so the expected value of the check in the other envelope is more than the value of the check in yours, so you should switch whatever x may be. B contains either 2x or 1/2 x, which is what we saw. Each possibility is equally likely. The expected value is 1.25. This conclusion cannot be right, but it is right. Applying the standard expectation formula, you calculate the expected value of switching to 1.25x. Obviously, this is absurd. It is not absurd. This is exactly what it is. It's 1.25x. So there's a camp that's trying to explain why there can't be 1.25x in the other envelope, and they convince themselves that they're right.